How's the take-home mini exam going? Anyone making any progress on that? When's it due? When? Oh, next time we meet. We've got a lot to do then. Okay. Any questions over homework or anything else? Anything? Questions over homework or anything? Okay. This is what we ended class with, right? And I turned it into a quiz, and that didn't work out so hot, so we turned it into a bonus, right? So how do you find the angle between two planes? Just to recap, how do you find the angle between two planes? You have to find the normal vectors for each of these planes. How do you find the normal vector of a plane equation like that? It's the coefficients of the variables x, y, and z. As long as the x, y, and z are all moved to one side of the equation. So like for this one, the normal vector, I'll call it n1, would be the vector 1, 1, 1. And then for this one, n2, the normal vector would be 2, negative 4, 7, right? And then what you do is you just find the angle between these. So you use the formula theta equals cosine inverse, blah, 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 right? Okay. Did you find what you're looking for? No? Okay. Please do. All right, so that's what we ended class with. We're not done with 10.5. We're actually supposed to start 10.6 today, or 10.6 and 10.7, so we're a little behind. All right, so this is a really important concept right here. Finding the line of intersection of two planes. So let's say we have two planes, and I forgot to bring my plane today, so I'm going to have to use a different one. So let's say we have two planes, right? If they intersect each other in a line, right? They form a line where they hit each other. What we'd like to do is be able to figure out what the equation of that line is. So here's the visual of what's going on. We've got two planes sitting here. Right? Two planes. And they hit each other in a line. Here's the line. Now that line extends forever in each direction, right? And since it's a line, I should be able to find the vector equation of it, right? That's what we did last class. There should be some vector equation for this line. And all lines, when written in the vector form, can be written this way. Right? So the only thing we needed again to find the vector equation of a line was what? A point, so that we could come up with this vector, and then a direction vector, which was the v, and then we were in business. So looking back at this picture, we need to first have a point, right? Do you think that if someone gave you these two planes, gave you the equations, do you think you could find a point on that line? Well, it would be a point that satisfies both equations simultaneously, right? Okay? So we could get a point. It seems like it would be relatively easy to do that. But what about a direction vector? How are we going to get the direction vector of this blue line? Well, the way we do it is first to take a look at the normal vectors of these planes. So try and just focus your attention, first of all. This green plane, that's a normal vector, right? And the normal vector is perpendicular to the plane. And that normal vector can slide anywhere I want on this plane, right? No matter what, move it around. Just can't change its direction. Then I take the normal vector of the other plane. Try and come in on the side and take a look at it. It's not perfect, but good enough. See the orange one, right? That looks normal, like this. No, sorry, it looks perpendicular to this plane. So if we take those two vectors, the two normal vectors, let me spin this around. And now what I'd like to do, I'm trying to spin it so you can see it a little easier. What I'm going to do is I'm going to slide those normals around. I'm going to move them. And when I move them, I'm going to move them so that they're both, the tails of both of them are touching the blue line, right? Which I'm free to do because they're vectors. And I'll take the other ones out of there. And do you recognize what would happen if I cross those two vectors? You get a vector that's perpendicular to both. And that perpendicular vector that we would get, this little red one, did you see it pop out right there? Guess what? It lies on our line. Actually, I shouldn't say it lies on the line. It points in the same direction as our line. Understand? So if someone gives you two planes and asks you for the vector equation of the line through the two planes, you get a point first, which we'll do. And then to find the direction vector, we'll have to take the two normal vectors of the planes, cross them, and that will give us v. Understand? All right. I believe the next part is an example. So find the vector equation of the line of intersection of these two planes. So I need R naught and I need V. So let's start with R naught. R naught, we will get this by finding any point of intersection of the planes. That means you need to give me some x, some y, some z, right? Give me an x and a y and a z that satisfy both of those at the same time. So do you remember how we did this before, or how we would do something like this? You could do a system of equations, right? You have two equations. You have three unknowns, which means one of the variables is kind of free. You're not going to have a unique solution in this case because you have more variables than equations. So you do something like this. You could set up the system, but how about we do this instead? How about I just try this? What if I just let z be 0? Okay? What would happen if I let z be 0? What would those two equations reduce to be? X plus y is 5, and then 2x minus 4y is what? Negative 10, and then I'm sorry, not equal negative 10. Equal 10, so move that over so we get this, right? Now you have a system of two equations and two unknowns. And now we should be able to solve that, right? So if I were doing this, I would do like an elimination or something. Of course, you can use matrices and do all that stuff, but if I'm working quickly, I'm just going to multiply the top one by 2, negative 2, sorry. Why am I doing that? Because the x's will cancel when I add down when I do this, right? So I'm going to multiply through by negative 2. So my new system of equations is negative 2x minus 2y equals negative 10. Are there any questions on what I'm doing, why I'm doing it? Or any questions? Who's going to win the Super Bowl? Anything that you want to know? No? You don't need to know? Okay. This is all right? We agree? So add straight down now. If you add down, what do you get? Negative 6y equals 0. And that means what? Y is 0? So now I have two of the three variables solved for. X was 0 when z was 0. When I let z be 0, that forced y to be 0. And now you go back and get x. So I can use any of these equations to get x. Doesn't matter which one. So why don't we use this one? X plus y is 0. X plus y is 5. So now using x plus y is 5, I have x plus 0 is 5, which means x is 5. So my potential point is the point 5, 0, 0. Everyone understand that? That's the point. That is a point that lives on the intersection. Should we check it real quick? Let's check it real quick. If I plug in 5, 0, 0, is the first one true? If I plug in 5, 0, 0, is it true? Well, those are gone. 2 times 5 is 10. 10 minus 10 is 0. That works. So that's a point that lives on the line, isn't it? Since that point lives on the line, I can draw a vector from the origin to that point. That'll be R naught. So I know what R naught is now, right? I'll put it up here. R naught, the vector, is the vector 5, 0, 0. We good?
Negative 5 if you're taking the x, 0 from the x.
What did I do? No, it's just, the 0 right here just goes away. I mean, it's adding nothing. All right, so now what? We've got R naught. What now? We need to find a vector that points in the same direction as our line, or as the line of intersection. So how do we get that vector? Take the normal vectors, cross them. That vector is guaranteed to run in the same direction as our line of intersection. So first part's done. Next part is to find V. V will be equal to the normal of the first plane crossed with the normal of the second plane. What is the normal of the first plane here? 1, 1, 1. Cross that with the normal of the second plane, which is 2, negative 4, 7. And then we do the cross product, right? I'm going to do that cross product over here. Getting kind of tired of doing cross products. All right, so let's see what it would be. The answer is a number, vector. What is it? Vector. And let's see what this would be. Cover this up. 7. Take away negative. So 7 plus 4. What? 11? 11. Okay, cover up this one. Let's see. 7. Take away 2. That's 5. But then change the sign. So negative 5. And then this one. Negative 4. Take away 2. Negative 6. Don't change the sign. Just leave it. That's it. That vector should be pointing in the same direction as our line. And so now I'm going to write down the vector equation. The vector equation of our line should be R of t equals R naught, which was 5, 0, 0, plus t times the vector v, which was 11, negative 5, negative 6. And then we just put it all together, right? Distribute the t through and then add the two vectors. See, one volunteer. Give me one volunteer for the answer. Not all at one time, please. Don't speak over each other like that. Come on, let's be polite. Anyone? Go ahead. Oh, we got one. Go ahead. 5 plus 11t. Negative 5t. Negative 6t. Anything else I should write here?
T is an element of all real numbers.
T is an element of all real numbers. That's just to clarify for everyone that I'm not drawing a line segment here. I'm actually drawing the entire line. Remember, the planes extend forever, don't they? So that line of intersection extends forever also. If you don't restrict, well, if t is allowed to be everything, you should draw everything on that line. If you don't put anything, then it's unclear as to what you want t to be. All right, we good? That's how you find the intersection, the vector equation of the line of intersection of two planes. Distances. Now, I've always found this section particularly interesting, almost amazing, because of the difficulty of the problem that we're going to be able to solve with relative ease. How do we find the shortest distance between a point and a plane? So a plane lives in three-dimensional space, right? Here it is. We have some point sitting in space. Let's say the camera is some point in space. And I'm going to take this plane, I'm just going to, here it is, right? What is the shortest distance between the camera and this plane? Well, how about this? Let me try this a little easier. This wall is a plane, right? What's the shortest distance between that camera and this sheet? Is it over here somewhere?
Wherever it gets it first.
Yeah. What do you mean hits it first?
Draw a line.
If I draw a line from the camera to the plane? Okay, so but I could draw a lot of lines. Where's my big ruler? There it is. So if I draw a line, you're saying from the camera straight to here. So there's the camera. Right here, this is a straight line. Straight to here. There, I just drew a line that was from the camera straight to here. Perpendicular to what? That line coming out of there has to be perpendicular to this? To the plane? Oh, so I've got it like this. And I've got to somehow move this around until this almost points right at the camera, right? Something like that. I think it's easy to see because we have a flat wall here, like vertical wall, and we have the camera. It's the same concept though, but imagine now this plane is not flat. Imagine this plane is now, over here like this. It's the same principle. Imagine a vector sticking out and I just need to move it around until I can point straight to the camera, right? But the thing coming out of here has to be perpendicular. Understand? That's a hard problem to do. I mean, if you just think about it. How do we find that shortest distance? So there's a little bit of a construction that we have to put together first to convince us of the answer. And I'm going to do it visually first. And that shouldn't be there. Here's an arbitrary plane sitting in space. You see it? And I have some point. This could be anywhere, so it doesn't matter where I rotate this, right? Just got arbitrarily got a point and a plane. Starting with that, find the shortest distance, 2 feet, 3 miles, whatever it is. Find the shortest distance between those two. So what we'll do is we will start to do this by just picking some point that lives in the plane. Can you find a point? If someone gives you the equation of a plane, can you find a point on that plane? Yeah, it's any x, y, and z that satisfies the equation. So finding a point that lives on a plane is very easy for us to do. So that would be easy, right? Okay. Now, the next thing we would do, or that we could do, is we could draw a vector that goes from that point to the point we're trying to get to, right? How do you find this vector? Take the coordinates of this point, subtract the coordinates of this point, and that creates that vector, right? So that should be easy for us to do also. Now, we're going to just look at and investigate the normal vector of the plane. The normal vector of the plane, this is not very good. The normal vector of the plane would be perpendicular to the plane, right? And it's a vector, so it can be moved around. I'm going to move it like this. Okay, well, what I need to do, start this thing over. So I'm going to move that normal vector, or sorry, not the normal. Here's the normal sticking out of the plane. I'm going to take that vector that went from that point to that point, all right? And I'm going to slide it so that it touches the bottom of the normal vector, right? And then I'm going to do this. And I'm going to take the original vector out. Do y'all see that? Can somebody tell me, just in layman's terms, not a formula, but in layman's terms, what this distance, I think I use little d, what that distance would be? It would be the component of the blue one onto the red one. So remember we talked about vector projections? Okay. The projection of the blue one onto the red one would be a vector going from here to here, right? The component of the blue one onto the red one is the length of that vector, isn't it? So if I can just come up with this vector right here and take its length, then that would be d, yeah? So I want the component of the blue onto the red. Understand that formula, or that idea? Now we have to actually come up with the algebraic formula for it. That's just the visual of what's happening. All right, so first we're given a point on the plane, or we're given a point, x1, y1, z1. And we're given the equation of a plane, ax plus by plus cz plus d equals 0. All right, so this is given information. Someone has to give us this. Go back to my picture here. Back it up. What did I say the first thing was that we were going to need to do? Find a point on the plane, right? So here's how I'm going to do this. I'm going to find a point on the plane. And let's call that point the point x naught, y naught, z naught. Is that okay? So this point right here is x1, y1, z1. We're going to pick some point on the plane. This point we're calling x naught, y naught, z naught. And then what did we do? Next? Create a vector that went from here to here, right? That vector that goes from here to here, we are going to call that vector b. Okay, we're going to call this vector b. And tell me up here the formula for b. b would be the vector, this one minus this one. So x1 minus x naught, y1 minus y naught, z1 minus z naught, right? This is making sense to you? And then we're going to shift or look at the normal. Here's the normal vector. Do you know what that normal vector is? This normal vector n is actually given by that equation over there, isn't it? It's ABC. Coefficients of x, y, z. All right? And then what we said we would do is we would shift the b vector over. So b hasn't changed, right? b is still the same vector. And then we're going to project it onto the red one. So what is this distance in terms of everything I've written on the board here? Do you remember the formula for component? What is the component? Look in your notes. What is the component of u onto v? What's the formula we have for that? U dot v over the magnitude of u? V? V. Look in your notes, right? Double check. That look right to you? That represents the length of the vector that you get when you project u onto v. Here we want the length of the vector when you project which vector onto which vector. So d, the distance. Let me check up here if I use little d or big D. Hold on. Big D. Okay, so the distance, this distance right here, from here all the way down there, we call that capital D. It should be equal to the component of what did you say? What onto what? B onto n, right? We are taking this b vector, which is here, we are projecting it onto the red vector, which is n. I hope that makes sense. And then what is this by definition? N dot b. Could I do b dot n? Yes, doesn't matter. But at the bottom is magnitude n. Oh, magnitude, yes. Yes, absolute value. That's how we get rid of the negative distance part. Because we'll measure distance as always being positive, right? So that's it. That's your formula. Okay? Understand? Let's do an example. That's basically what all this stuff up here in the notes says. All right, that's the formula I'm going to work off of. Now, you can actually simplify that formula. You can actually do the dot product of these two, like dot out n and b, and you come up with this. And yeah, that's great. But I like the other formula. This one right here. It's much cleaner. Okay. All right. Now we test to see if you can think a little bit outside the box here. The formula I just gave you was the formula for finding the distance between what? The shortest distance between a plane and a point. Look at this question. Find the shortest distance between these parallel planes. So I'm telling you have two planes and that they are parallel, right? So, I don't know, maybe any of these, right? These are parallel planes. Find the shortest distance between them. What people always like to do in this case, they always do, well, what they are tempted to do is they say, okay, look at this equation. X plus y plus z is 5. Over here, they say, hey, look, I can divide everything by 2, and I would get this. Don't write this down, by the way. I get this, right? So look at this equation, this equation. Very similar, aren't they? In fact, they have the same normal vectors, don't they? 1, 1, 1, 1, 1, 1. The normals are pointing in the same direction, which means they're parallel, right? Planes. So people go, oh, well, the distance obviously must be 5. Right? 5, 10. Forget this one. I rewrote that one to here. They say, oh, the distance between the planes must be 5. That's wrong. That would be way too easy. And it's incorrect. So, how would you do this? Anyone have any ideas? You have two planes. They're parallel, right? Here's a plane. Here's some other plane. I'm going to put this other plane pretty far away from it. Those two planes are parallel. Trying to find the shortest distance between the two.
Just find a point on one of the planes.
Okay, so pick a point that lives on one of these planes. Whatever you want, right?
Would you prefer to go through from a corner? Corner to corner?
Well, these planes extend forever, right? So we can't really cut them off. I can't draw it extended forever. So you're saying pick a point on one of the planes, and then what?
Now to solve the plane. 0 plus 0 plus 5 is 5.
Yeah, so I'll have to get a point. I agree. Well, let's get one in a second. But what are you going to do with that? Why are you doing that? Picking a point there.
Well, once you find the point and you have a second plane, then you can find the short.
That's right. So this is what you have to, this is the connection you have to make, okay? If I'm trying to find the shortest distance between two parallel planes, that is equivalent to me asking you the shortest distance between any point on this plane and this, right? All the points on this plane have the same distance, shortest distance to this plane, don't they? So by giving you the entire plane, this is actually overkill. You don't need all that. You just need one point here, don't you? Yes? Okay, so first step is to find a point on one of the planes. So we're going to find a point on one plane. And how about on plane 1? Give me a point that lives on plane 1. I think you said 0, 0, 5. Everyone agree that point lives on plane 1? So picture-wise, I have a point here, 0, 0, 5, right? That lives on this plane, this first plane, which is up here somewhere. There it is, okay? The fact that it lives on the whole plane, I don't care about anymore, right? Then parallel to it down here, I have my second plane, right? Plane 2, here's plane 1. So I'm now trying to find the shortest distance between that point and this plane. So what do? What's the next thing? Find another point on the second plane. Anything I want. So I'm going to find a second point over here. So point on I'll say plane 2 is the next thing I'm doing. So what's a point on plane 2? 0, 10, 0. Good. I'll go with that. The good news is you have an infinite number of points you could have picked. The bad news is that when I'm grading these, everyone's going to pick a different frickin' point, and so I'm going to have to check to make sure you did it right. But we should all get the same distance, right? Okay. We should all get the same distance. Any point. Yep. That's the beauty of it, because the next thing we do now is we draw a vector that goes from here to here, right? And that vector we call what? B. This will be B. So let's go ahead and find what B is, and I'll put it over here. B is the vector, what? 0, -10, and 5. So remember, we're going from this point, which was this one, to this one, yes.
What did you call B vector again? B with an A? It's not the normal vector?
It's not the normal. No, it really doesn't have a special name. It's just it's a vector that connects 2 points on the plane. Then we take the normal vector, right? The normal vector is just pointing up, right? So my normal vector is here, it's pointing up, right? What I want to do is imagine that normal vector is going to point straight up to that, right? So my normal vector points up. Do I know how long the normal vector is? I mean, I can measure it. I could actually look at the normal vector, couldn't I? And measure how long it is? But is the length of the normal vector, is this length here of the normal, the distance between these? No, not necessarily. But that's why we need to do the projection, all right? So this normal vector, it might go right through that point. It might be really long like that. This is my normal vector. And what is our normal vector, by the way? The one for plane 2. Let's just use 2, 2, 2. Yes, I could come through and divide this through, but 2, 2, 2. Okay? So if we take this red vector, don't have enough reds here. We take this red vector and we slide it to the normal, right? And then project it over, then this projection vector right here, its length is the distance, which is just the formula that we just came up with. How many of y'all see this visually, what's happening? Show of hands. If you don't, it's okay, but yeah? If you're just one of those people like, give me the formula, then you don't have to worry about all this, but you better know how to get B, how to get N, and then do the computation. All right, so here we go. The distance we want is the component of B onto N, which is the absolute value of N dot B over the magnitude of N, which equals for us, what's N dot B? Well, dot products are super easy, aren't they? Easy? I don't know if I should have used that word. Quick? So what do you get when you dot N and B together? 2 times 0, so nothing, plus 2 times -10, which is -20, and then plus 2 times 5, which is 10, all over the magnitude of N, which is the square root of this squared plus this squared plus this squared, right? So the square root of 4 plus 4 plus 4.
Why are you multiplying the natural, why is it 2?
Why is what 2?
Like when you do the n.
Okay, because we were looking for the normal vector of plane 2. Maybe I should have done that. Normal vector of plane 2. Plane 2, the normal vector is 2, 2, 2. Yes? I could have used 1, 1, 1. Yes?
Why is it a -10 and
Oh man, I erased it. When you, oh well, no, you can do it here. The b is the vector that goes from here to here. So you do 0 minus 0, which is 0. 0 minus 10 is negative 10. 5 minus 0, 0. I mean, sorry, 5 minus 0 is 5. Got it? And let's see, what this turns out to be up top is what? Negative 10, then absolute value. So 10 on top over root 12. Whatever that is. The shortest distance between those two planes is 10 over root 12. Well, they're parallel planes, so the shortest distance is the distance, right? Right. Questions? Yes?
Finding the magnitude of the created of the vector b, and then just doing the sign. Oh, but we don't know that.
You would have to know some angles. You would have to know some angles. But you might be able to do it that way, actually. But you would have to bring in some other formulas into it. Actually, in the next problem, you're going to see we're going to do something just like that.
And then you can solve for those angles too, right? After you get the distance.
Yeah.
That's cool.
Yeah, you could. You could figure out these. But you really wouldn't need to know. I don't see a value in knowing the distance or the angle here. Only because this was an arbitrary point. So unless that point has meaning to you, then. But could you? Yes. All right, now we're going to go talk about the last sort of distance that we want to be able to do. And that's finding the distance between the shortest distance between an arbitrary point and a line. So this is even more challenging. Because think about this line in three-dimensional space. Think about the camera as being a point again. What is the shortest distance from this line to the camera?
Wouldn't it be the same magnitude?
Yeah, but do you see the problem we're going to run into? If I'm forced to be on this line, there are an infinite number of perpendiculars, aren't there? It could be anything, right? So I'd have to try and move this and then somehow get it to be the one pointing up like that. Do you see that? It'd be difficult to... The thing about the plane that was great is that the normal vector could be slid around. And so I could always move it and point it to the camera. With the line, it's a little different. Do y'all see the challenge? Planet. That's a planet. You have a rocket, a path of a rocket. You're going to pass by this planet in three-dimensional space, right? What is the shortest distance going to be? Right? Or maybe we should do it another way. You have a planet, us, okay? Here's us on the planet. And you have something coming towards us, right? It's going to pass by the Earth. And they say, oh, it's going to come within a certain distance, isn't it? Well, this is basically this problem. You have a point, which we're going to say is the planet, and you have a line, and we're trying to find the shortest distance between them, right? Now, yes, the path of the comet or whatever might not be a linear thing, but just generally, is this okay? All right. All right, so I'm going to show you the geometric construction first. There it is. For the sake of simplicity, we're going to look at it two-dimensionally. So that means, like, if we've got our line sitting in space, and we've got our point, which is the camera, there is a way that I could move around and look at it from a certain point of view where it would look like this to me, wouldn't it? If I'm allowed to float around the room, I could eventually get it to look like this. So what I'm going to do here to try and find the shortest distance, which, by the way, is that distance, right? In order to do that, if all I have is the point and the line, is first I'm going to pick a point on that line. You see that point? There we go, Q, call it Q. I'm going to pick another point on the line. We should always be able to come up with 2 points on the line, right? If someone gives you the equation of the line. Okay, we should be able to pick 2 points in time, or 2 points on the line. Then I'm going to draw a vector, which is the vector A. So would you agree that the vector A is a direction vector? A is just the direction of the line, isn't it? So A is actually parallel to V. Remember when we talked about vector equations of lines, we have this general equation. V is any direction vector, right? Pointing in the same direction as the line. So if I create a vector that goes from 2 points on the line, that vector A has got to be parallel to V. Okay, just keep that in mind. Now what I'm going to do is I'm going to create another vector, which I will call B. That vector connects some arbitrary point on the line to the point that we're interested in. So far, okay? Looks kind of similar to what we just did a minute ago, right? Here's what I'm interested in, right? D. Everyone see the right triangle? Now I'm going to put something up here and see if you agree with this. If this is a right triangle, sine of theta would be opposite over hypotenuse, right? The opposite side would be D, which is what we're looking for. And then the hypotenuse isn't the vector B, it's actually its length, isn't it? The length of B is the hypotenuse? Yes? Okay. Well, that means that D must be what? Solve for D here. Magnitude of B, sine theta. Yeah? That looks like a very clean, easy formula, right? If I want to know the distance, all I need to know is the length of B, which is some arbitrary vector that we came up with, right? We picked a point, we drew a vector. Does that seem like we could do that pretty easily? But then, times sine of the angle between A and B, right? Is that going to be easy to get that? How would you get that angle? Well, it's the angle between what? Angle between A and B, right? So you would do like arc cosine and all that stuff, but there's an even cleaner way. Watch this. And this is like magic, voodoo magic. Not really magic, but just tell me whether or not you agree with this. I can multiply this times 1. Yeah? Okay. Here's the 1 I'm going to multiply it by. Is that a 1? Yes? Okay, now what was already there is this. Right? That's what was there already? Anybody recognize the numerator? That is the magnitude of A cross B. If you look back in your notes, the magnitude of A cross B is this. So what I did is I said, you know what? This is fine. That's great. I've got a good formula. But finding sine of theta, it's going to be work. Too much work. I don't want to have to go find theta and then go find sine of it. That's too much work. If that was magnitude of A times magnitude of B times sine of theta, that would be magnitude of cross product. But I didn't have that. So I introduced it on top and bottom to make it happen. Clever, isn't it? Isn't that clever? So D then is magnitude of A cross magnitude of B, or sorry, magnitude of A cross B over magnitude of A. That is the distance. Shortest distance between a point and a line. That's what the notes say up here. Oh, no, they don't. Next page, maybe? No? Hello? Where is it? Oh, it's down here. Here we go. That formula is what? This one right here? What about it? This D, this right here is the distance from the shortest distance between a point and a line. But you have to understand what each of these vectors are, right? What is B? Tell me, like in layman's terms, what's B? What is that vector? It's a vector from a point, any point on your line, to the point we're trying to get to, right? And what's A? any direction vector of the line. So A may as well be V, right? A may as well be V, this V. It's going to be very, very easy to find this distance. But the formulation of the formula, I think, is pretty cool. All right, here we go. Let's do an example. This is the formula. Find the shortest distance between that point 3, 6, negative 7 and the line that goes through the points blah, blah, blah. So I have a point sitting out here in space. The point is the point 3, 6, negative 7. Then I have 2 points that live on a line. The point 0, 3, 5 and the point negative 4, 9, 10. There's a line that goes through these, right? Trying to find the shortest distance between that line and that point. According to the formula, the distance will be equal to A cross B magnitude over magnitude of A, right? That's the big formula from this. What's A? What's the vector A? How would we get it? Where is it? Show me, point me to.
From 0, 3, 5 to...
Okay, so if I just create a vector that goes from here to here, A, that's how I define A, right? So go ahead and let me know, what is A? A is
negative 4,
-4,
6,
6,
5.
5. All right, good. Got one of the two pieces. Now what do I need? Vector that goes from any point, right? Any point on the line to the point in question. So why don't we use this one? And that's going to be B, isn't it? What is B for this problem? Oh, just leave it. Don't worry about it. What is it? 3, 3, negative 12. Any questions on that? Once you've generated the direction vector of the line and a vector from any point on the line to your point, you're ready for the formula. You don't have to go draw the right triangle, do that. That's what the formula is there for. So all I have to do is take the cross product, take the magnitude, divide it by the magnitude of A, I'm done. So let's go ahead and get A cross B. Any questions though? A cross B, I'll do it right here. A cross B, I'll do magnitude in a minute, is a vector. What's the vector? So we got to do the cross product. Cover this up. I think we'll need a calculator for this. Okay, first one is what? 57? I don't know about that. Hold on.
I got negative 87.
Okay, we're doing 6 times negative 12, negative 72, take away 15, so negative 87. And then 48, take away 15, 33, but then change the sign. So negative 33, I hope. Last one, negative 12, take away 18, negative 30. Show of hands, how many of you agree? If enough of us agree, it's right. And then the magnitude. We have to find its magnitude, which is the square root of all of these squared added up. Let's get that as a numerical answer. In other words, go figure out what that is as a decimal, and I'm going to check our work. We're crossing -4, 5, 6. Oh, 6, 5. With 3, 3, -12. I'll make this a little bigger so you can see it. There's the cross product. I take the absolute value of that answer and multiply it times 1.0. Whoa. Anyone get 97.765 for the top? Yes? All right, so we're ready to put this in here. The magnitude of the cross product is approximately 97.765. That's the top. And then the magnitude of A. What's the magnitude of A? This square plus this square plus this squared, right? What is it? Oh, I was pointing at B. Sorry. This. Root 77. So go ahead and do that. 97.765 over root 77, which is approximately 11.14. There we go. Feet, miles, whatever the units are, it's not given in this problem. What do you think? Yeah? So that should be the shortest distance right there. Now let me, what time is it? Man, ate up so much time. Let me take a look at your exam problem real quick, that last one. The what?
It's not the sum of the coefficients of the ij. It's not simply the sum of the square root.
Yeah. Take a look at number 5. Has anyone started 5 yet? Tried it? Okay, officially, as of right now, you can do this problem. All right? I'll just talk through it. I don't want to give it away. Find the vector equation of the line. What does that mean you need? A point and a direction vector. R naught and V, right? R naught and V, you're in business. Find the vector equation of the line that passes through the center of a sphere. So the center of a sphere is a point, right? So we're trying to find the equation, vector equation of the line. And I'm telling you that the center of this sphere lives on that line. And another point on the line is the point of intersection of this line with this plane. So this is one point on the line. Everyone understand where that comes from? The other one, the other point that lives on your line, because you only need 2 points to define a line, is the intersection of some other line with some other sheet of paper over here. Now the drawing of it is over here. This is the actual solution, and you've got a line. This orange line is the one that's given. It hits this plane somewhere, so you're trying to find the yellow one. It's the one from here, from this point, to the center of this sphere. I hope that makes sense. You got to make the rest of the sense out of it, all right? The other thing I wanted to show you,
It goes from 5 to 5. Oh. That's supposed to be 6.
where is it? I used to give this to my Cal 3 class. I'm not going to do this. But if you're interested in something to work on, it would take many, many hours to do. These are the things that all students should be able to do after this section. Oops. Find the vector equation of a line given 2 points. If I give you 2 points, everyone should be able to find the vector equation of a line. Find the vector equation of a line through a given point and parallel to some given line. Find the vector equation of a line through a given point that's perpendicular to a given plane. These are a bunch of different weird combinations of things that you should be able to do to find vector equations of lines. Each one of them presents its own challenge. And then this is examples of how to get equations of planes. And then I give a list of examples with pictures of all the different scenarios. I used to give that as a take-home assignment. It's very, very long. If you're interested in this just as a challenge exercise, I'd be willing to give that to you and perhaps use it as some sort of credit later in the semester. But that would be, you would have to take the initiative to go get that from me. Okay? I don't believe that's there. No. No. I don't know. I probably would put a due date. I just wouldn't want people at the very end of the semester trying to like cram that in at the very end just because they need points. Yeah. So if you're interested in that, let me know. After class, email me or something. Come by my office. How about that? Why don't we make it you have to come by my office? That way you have to actually come sit down with me. That'd be awesome. Nobody's come in for help, really. We're moving on to 10.6. Was the homework there? Oh, you have the homework. Never mind. Okay, for this particular section, I was talking to one of your classmates earlier, and we were just talking about Cal 3 in general. And you know, if you're sitting there like wondering why they call this Cal 3 when we still haven't done any calculus yet, right? No limits, no derivatives, no integrals. It is very, very shortly around the corner. 10.7 is where we start bringing in derivatives and integrals and things like that. But we're just trying to get a lot of these formalities out of the way first. 10.5 was the first big section that had some real meat on its bones, because I can ask you some pretty tough questions out of 10.5. There can be some pretty hard problems given to you. I mean, it's relative, right? This section, though, I'm going to be talking a lot, asking you to look at something and try and visualize it. At the end of the day, there's only a few small things that you need to be able to do out of this section. We could spend 3 weeks, 4 weeks learning how to graph these sorts of surfaces by hand. It's a pain in the ass, and this is where technology is worth having. All right? So I'm going to start by reminding you of some important equations that we ran into in different classes before this. In two-dimensional space, the equation x squared plus y squared equals r squared draws a circle, right, with some radius, right? That's what it is two-dimensionally. No surprises?